Good day. We continue our lecture for design for strength, and this is lecture 12. In the last class, you remember that we have been discussing about the equations related to the shape stress design in case of fatigue loading, and these are the Gerber line, the Goodman line and the Soderberg line, where you remember that the abscissa was the mean stress and the ordinate is represented as the stress amplitude. Now, if we consider this line, then what we can see is that if we look for the line, that is we considered this is a sigma mean stress and this is the sigma A, that is the stress amplitude, and let us consider a line which represents the Soderberg line. So, in this case you can understand the coordinate of this particular point should be sigma y by 0, because you know the Soderberg point or the Soderberg line is actually guarding against the yield criteria, and this we understand as 0 comma endurance limit for the machine element. So, if we consider the equation of this line, then you can see very easily that we get an expression something like this: sigma A minus just an equation of straight line, epsilon equals to what? 0 minus sigma epsilon sigma E sigma yield point minus 0, and this is sigma mean minus 0, and this if you simplify comes out to be sigma A minus sigma E equals to minus of sigma E by sigma y into sigma m. So, if we simplify this relationship, we get a expression like this. So, this is the relationship what one should consider when we are designing for Soderberg criteria. Now, in the similar manner, what one can see that we can have the equations developed for the Gerber line or the Goodman line, what we have just shown just in the last slide. So, you can see that in this case any point, if we consider any point A which can be, for which the mean stress is sigma n and the stress amplitude is sigma A, this can be related with the material property like sigma ultimate or sigma yield point or sigma endurance by the relationships generated from the equations of the straight lines as shown in this slide. These equations, if we look, then it is something like this. One, the first equation Soderberg criterion we have just developed. In the similar manner, one can develop the Goodman criteria. You can see there is no change except for the fact that sigma yield point is replaced by the sigma ultimate. And this last equation sigma A by sigma endurance plus sigma m by sigma ultimate whole square equals to 1. This is called the Gerber parabolic relationship, and out of these 3 equations one can utilize either of these 3 to go for the design for the fatigue strength, where one has to know the value of the sigma A, that is the stress amplitude, one has to know the value of mean stress and the material property. One should take into account of that all the factors which changes the endurance limit of the material by certain factors which will be multiplied by the endurance limit to get the endurance limit for the machine member, which we have represented as sigma E m. Now, one thing we will see right now is that in this particular expression you see that same Soderberg criteria has been written, where we consider a factor of safety F s. So, in that case the equation changes as sigma A by sigma endurance plus sigma mean by sigma yield point, that equals to 1 by factor of safety. How it comes? It is very simple, that this factor of safety what you are considering, suppose we consider F s over here, F s over here, that means this is the material property reduced by an factor of safety. So, this factor of safety goes up, and then what we get, that means this factor of safety coming over here, and then if you divide by factor of safety, then ultimately what you get? Ultimately you get a relationship of this nature. So, here in this case what you can see, that in for all the situations you are having the equations of Soderberg criteria, equation for Goodman criteria and equation for Gerber criteria, including the factor of safety. Here once again we have written the Soderberg criteria and Goodman criteria considering the factors K f and factor K t, which is coming over in the Goodman criteria. Let us look into this particular feature. Whenever we are considering a ductile material, then you should remember that always the stress amplitude sigma A should be multiplied by the K f, or what we consider as by K f what we consider as the fatigue stress concentration factor, for which we had a detailed discussion in the earlier class. However, whenever we are considering a brittle material, then in general people use the Goodman criteria because of the fact that the guiding material property becomes the sigma ultimate, whereas in the Soderberg criteria we consider this sigma yield point, because we always know that for the ductile materials the sigma yield points are the material is a material property which is normally utilized. So, in the Goodman criteria you can see that K f is multiplied as it was multiplied in the Soderberg criteria. However, we are multiplying an additional thing, that is a K t with the mean stress, whereas we are not multiplying an K t in the mean stress for the Soderberg criteria. The reason is that this theoretical stress concentration factor, as we have seen earlier, is is something which is a very localized phenomena, and in case of the ductile material, the stress concentration due to the stress concentration effect, what happens, there is an this particular material, even if it is in a higher stress, it gets some locally stress relieved and it do not affect the material to that extent as it affect in the case of the brittle material. So, thereby it is customary that one should take up the value of what you call the theoretical stress concentration factor in case of the sigma mean, whereas in case of the ductile material one need not consider these values of the kT for the design purpose. So, the equation what we got in the earlier equation, means these equations what we have just seen is being modified by the certain factors like Kf and Kt Kf in case of the brittle material and Kf in case of the ductile material. However, we have not spoken anything about the Gerber line, one can utilize in the same manner. However, there is no bar in using the Gerber line, but people utilizes mostly the Soderberg criteria and the Goodman criteria because of the simple linear relationship instead of going for the calculations through parabolic relationships. So, you can see that this Soderberg criteria for ductile material and Goodman criteria for brittle material are quite popular in the fatigue design. Now, here is a case where we consider the situation when we are having the combined normal and the shear stress. See, one of the situation comes out to be this way, that suppose we write a equation of the form stress amplitude by endurance limit mean stress by ultimate stress equal to 1 upon Fs. Just a little manipulation of this equation, you can see that you multiply all through by sigma ultimate. So, we get an expression of this type. Now, once we get an expression of this type, you can see that this particular factor coming out to be something like this. Now, if we identify this factor, you can easily realize that sigma ultimate by factor of safety is nothing but a concept of a design stress. So, once it is a concept of the design stress, why not to call this entire equation, this entire part of the equation is somewhat a stress which could be read as sigma equivalent, means the sigma ultimate divided by factor of safety. Anyway, we consider in the static design to be a working stress, and in the similar manner we consider for the fatigue design that sigma ultimate into sigma amplitude by stress amplitude by sigma E plus sigma m to be somewhat like an sigma equivalent stress. In the same logic, if we write down the expression for the shear stress, then what we get, that the expression comes out to be again in the form of tau ultimate by factor of safety, and we get a situation something like that, tau equivalent. So, what we will be doing with this sigma equivalent and tau equivalent? Let us see how we can do it. Let us take up a situation that all the mean stress and amplitude stress are being replaced as sigma equivalent and tau equivalent. So, that means all the loads which creates an stress similar to what we call as a normal stress, and all the stresses which creates a stress similar to the shear stress we call as an tau equivalent. So, very nicely we can find out from the tau equivalent and sigma equivalent a Mohs circle drawn from where we can get the values of sigma 1 and sigma 2. So, once we can find out the values of sigma 1 and sigma 2, then what we can utilize? That means, we can utilize either maximum shear stress theory or von Mises criterion. So, either of these two can be utilized to find out ultimately the desired design parameters. So, this way one can combine the both the normal stress and shear stress to get the design for the fatigue. Now, let us look into a small problem. I think you can see that a machine member has been chosen almost similar to what we called as a specimen for fatigue test, and let us assume that at the middle of the specimen, say a 5 kilonewton force is being acting and the shaft is continuously rotating. This shaft is having an rotation, any rotation, it is continuously having a rotation like this. So, once you are having a rotation and then acted upon by a constant 5 kilonewton, then what is happening? That you can easily understand that the fibers are getting completely reversed loading. And what type of loading it is getting? The predominant loading what it is coming into picture is the bending load, because of this 5 kilonewton the shaft will have a bending shape and it will try to rotate in the bend mode, thereby it will be having a completely reversed stress cycle of a tensile stress and a compressive stress. We have taken a material cold drawn steel for which the ultimate and the yield point values are given as it is given in this particular drawing, I mean particular sheet, and let us take a factor of safety 1.5, and let us also consider the surface is machine surface, and other data you can see, that means we can have the cold drawn steel 5 kilonewton constant force, then sigma ultimate 550 megapascal, sigma yield point 460 megapascals. You can see the distances, and another situation is that it has got a fillet radius whose R by D ratio is 0.1, whereby the large diameter to small diameter ratio is also given in the form D equals to capital T by 2, where capital D is the diameter of the larger portion and small d is the diameter of the smaller portion. Now, once we consider this particular machine member for design, we understand that what to design means we will be designing for the calculation of the diameters the corresponding fillet radius, etc., so that it can take up this 5 kilonewton force under the fatigue condition. Once we take up these ideas, then let us utilize our knowledge so far what we have learned, from which I think we will be able to calculate or able to solve for the given problem. Now, first of all, let us have a small sketch of the problem. Well, this is somehow the idea what we have got. Now, in this case, what we have can find out, as we know that the design is always based on to the weak sections. Here we can find out that here is one section, and let this section be C, and this CC and DD are the sections where we can find out that either of these two could be the points of failures. One here, because of the fact that the diameter is small, and at the same time due to the larger length it will be acted upon by a larger bending moment. Whereas, at this particular section you can see the bending moment will be small compared to what we get at D. That means, here the moment at C will be smaller than the bending moment. Let us write bending moment at C will be smaller than the bending moment at D, but at the same time we are having a change in dimensions, and which will create a stress concentration at this zone. Thereby, the introduction of the fatigue stress concentration factor in the equation just said, just discussed a few minutes back, we can expect that this C could be a critical section. Let us consider this to be the critical section with the logics just we have discussed and carry on our design. However, one should also try out, or one should look for some other sections which could be the critical section, such as the section D as I have shown in the slide, this section D as I have shown in the slide. But for the time being, let us assume this to be critical section, and we consider the design based on the section, the values of the bending moment based on this section. So, I hope that you understand the logic behind putting the critical section to be as the at the location C. Now, what we know first of all is that what should be the modifications of the stress concentration factors arising at C due to this change of the dimensions. Here it is given that R by D ratio is 0.1, and for R by D ratio 0.1, if we consider the design data book chapters, then you can easily find out from the graphs that KT comes out to be something like 1.72. I hope that you remember the KT, for which I had already shown you a typical curve. Similarly, KTS means when considering the shear, we can take up this value to be 1.48. In the similar manner, one can see the notch sensitivity for this value, this situation is coming out to be notch sensitivity for the bending, say this bending is 0.75. This also has been taken from the standard data book, and I am not going to show you this data book results. You can just go through it and find out those values. Well, these values are for the R by D ratio 0.1. Now, what is the bending moment at C? This is center 5 kilonewton. So, obviously, the bending moment at C comes out to be how much? 7.5. This is 2.5 at the bearing locations. It is 2.5 kilonewton. So, multiplied by the distance. So, 7.5 into 10 to the power 5 Newton millimeter, 2.5 and multiplied by how much? This is this dimension you can understand. So, that means this is 3, this is 300. So, 3 is 7.5 into the power 5 Newton millimeter. Please look once again that you should keep in these units, that I am trying to put all the force units in Newton, all the dimensions in millimeter, thereby the stresses handled will have the units in megapascal. So, once we get this values of the bending moment, then what you can find out, that bending moment mean comes out to be how much? 0. Bending moment, what is coming out to be stress amplitude, means moment is the mean stress and its amplitude is coming out to be 7.5 into 10 to the power 5 Newton millimeter. This mean stress is maximum plus minimum by 2, amplitude is maximum minus minimum divided by 2. So, this is maximum and minimum. So, what is the maximum stress is coming? So, M max is 7.5 plus and minus 7.5, this is the minimum. So, obviously, we get a value of M or the mean stress 0 and amplitude, not stress, sorry, the mean moment is 0 and moment amplitude is coming out to be the 7.5. So, means bending stress is 0 and what will be the amplitude stress? This comes out to be equals to, if we calculate, then you understand, 32 into M by pi d cube, and this comes out to be something like 76.4 into 10 to the power 5 by d cube ampere. So, this is the value of mean and this amplitude. So, keep a note of these two things and let us go to the another page. Now, the question comes that in this case, what should be the value of endurance for the machine element? That means, what is the value of sigma EM to be taken up. You know, we have introduced earlier that we can utilize the factors, something like the surface factor, we are having the size factor, we can have the load factor, we can have the temperature factor, and so on and so forth. So, first of all, we do not know the value of sigma endurance. How we find out the sigma endurance value? We know that this sigma endurance value from our previous lectures, we know that this value will be coming out to be something like this. Just okay, we consider this value of sigma endurance is 0.5 into sigma ultimate. Please look into your note what we have given earlier. Then we multiply this sigma endurance for the machine element by K surface, K size, K load, K temperature, and K miscellaneous. Now, for the given condition, we assume the surface to be machined. So, if we look, then you will be finding out that K surface is given by the empirical relationship 4.51 into 550, this is the ultimate strength, to the power minus 0.265. Once you calculate this value, then it comes out to be something like 0.847. Now, in the similar manner, one can find out that what is the value of K size. Now, K size, if you look to your earlier notes, you will be finding out that this is given by a formula something like this. But unfortunately, we have to find out the value of D. We do not know what is the value of D, because this is the task had been given to us to find out the value of D. One way, you assume a value just by an initial guess, and then it can be later modified. In the similar manner, you can have a assumption from the calculation based on the static force design. That means, what I mean to say is that you can have the idea of the design. Let me erase out this portion of the one which we have already taken care of. Okay. So, what I am just trying to say that in this case we know that sigma equals to m y by I, okay, or it is given as m by z, I by y is m by z. So, if we consider this equation, then what we can get, that this stress value one can find out to be what? this Z, if we can find out, the M we know and the value we know of the Z sigma, what should be the value of sigma? Let us take the value of sigma to be equals to 460, which is the yield point of the material. This is the sigma yield point of the material, from which we can find out the value of the Z. Now, here let us take M, this M let us take at the center of the bar to be on the little on the larger side. So, we get it is 10.0 into 10 to the power 5, and by substituting these values one can find out the value of D is something around 30 mm. This is from the static graph. That means, just to have an initial guess of the this particular value from the static design. So, we substitute the value of D as something like 30 and this gives us a value of 0.856. So, we have found out the surface K surface, we have found out that K size, but still this is little bit of an approximate value. Anyway, now after the intercalculation you will see that the results will be can be modified to a little extent by using some other factor. However, as because it is pure bending, K load comes out to be 1.0, and we have not talked about anything of the temperature. We have not talked about anything of the temperature factor. Let us assume to be something around ambient temperature, that means much less than this 300 degree centigrade. So, we can assume K temperature to be 1.0, and let us take K miscellaneous also to be 1.0. So, that ultimately what we get, that the endurance limit or endurance limit for the machine member comes out to be endurance limit for the material multiplied by how much, multiplied by 0.847 multiplied by 0.856 multiplied by 1 multiplied by 1, and this value we have chosen to be 0.5 to into how much, into 500 I am sorry, I think it was 550. Okay, it is not 500, as I have just shown in the last calculation, it was 0.5 into 550 multiplied by 0.847 multiplied by 0.856 etc. So, this gives you a total value of 199.43 megapascal. So, this is the calculated value of the endurance limit for the material. Now, let us find out the value of fatigue stress concentration factor. This Kf equals to, you remember the well known relationship, this Q into Kt minus 1 and putting out these values 1 plus q, we have noted down that q for bending was 0.75, this was 1.72 minus 1, that gives us the value as 1.54. This is a cold drawn steel material, and for the design of design for fatigue consideration, which criteria we should choose? Obviously, you know that the guard against the yield will be the best one. That means, the Soderberg criteria is a very common one for the ductile material, and one can use the Soderberg criteria for designing for the particular problem at hand. Now, it is a simple situation that we can put all the values in the Soderberg, all the values as this Kf, this sigma A endurance for this one, then we require the sigma A, we have already computed, we have to put the value of the sigma m. What more you require? You require sigma yield point, isn't it? So, sigma yield point we require sigma A, we require sigma m, we require sigma endurance limit for the machine element, machine member to be designed, and the fatigue stress concentration factor Ka. Kt is not required because we know that theoretical stress concentration factor may be neglected in case of ductile material, because the local yielding will relieve the stress. So, that is the reason the ductile material do not have any Kt in the design calculations. So, we are sure that we know this one, this one, this one, this one, this one, and thereby we can write down the Soderberg criteria to find out the design calculations. So, what is this one? We know that sigma A by sigma stress amplitude by endurance plus sigma m by what you call this yield point equals to 1 by Fs. You modify the stress amplitude by the factor Kf. So, what is sigma? This amplitude, this is equals to 0. So, thereby this term is not coming into picture. So, if we put all the situations in order, then 1.5, this is the factor of safety, is 1.54 multiplied by 76.4 into 10 to the power 5 divided by d cube into 199.43. What is this one? This is, just one second, let me rewrite this one neatly. Okay, this was 199.43. Which one is unknown? This parameter is unknown. So, after calculation one can find out d to be something around 44.56. So, just if you assume to be a 45 mm, then what you get? Now, here if you just take up a full figure, or the normally which figure you should take up? You should take up the value for the available material or the ingot in hand by which you can design in an economic manner. Okay. So, you let us take that this as 45 mm. Then what will be the other dimensions? So, capital D will come out to be capital D will be come out to be twice this thing, that means it will be 90 mm, and R will be coming out to be 0.1. So, 4.5 mm. So, here goes the final value of the design. You see, our rough estimation for the diameter was how much? 30 mm roughly, but now for the fatigue design considerations it comes out to be around 45 mm. Well, as I was telling that you can have a small iteration by again considering this 45 mm into the size factor and again recalculate the dimensions. However, that change will be not to that extent, because there is a cubic function involved in it. So, this is one example by which you can find out the dimensions of a machine element considering the fatigue design. Now, let us look into the same problem. We introduce just simply another torsion in the problem. You can see a torque have been applied, and let us assume that the varying torque comes out to be how much? This is coming out to be 100 Newton meter. This is coming out to be 100 Newton meter to 500 Newton meter. Now, you can see this is just simply a fluctuating stress. Okay. So, for which we can find out in the similar manner the stress amplitude. This we will call as shear stress amplitude and mean shear stress, and carry out the calculations taking the ideas from our previous design calculations. Now, let us have an assumption just to make short or cut short the all other calculations, that everything, the size factor, surface factor, temperature factor are remaining the same for this particular problem also. Only thing what we will be having, that it will be having a load factor, because in case of bending the load factor was 1, but in case of the shear you remember the load factor comes out to be around 0.577. So, if we consider this design once again for taking up the torsion included in addition to this particular 5 kilonewton force, then what we can find out very quickly is something like this. Okay. Now, we can quickly take up this idea that T mean comes out to be how much? 500 plus 100 divided by 2. So, this comes out to be 300 Newton meter, that comes out to be 300 into 10 to the power 300 Newton meter, and that means 300 into 10 to the power 3 Newton millimeter. Once we have to change all the dimensions to the millimeter. In the same way, we can have the stress amplitude TA 500 minus 100 divided by 2, and that comes out to be straight away 400 by 2, that means 2 into 10 to the power 5 Newton millimeter. This is very easy, you can understand very nicely. That means what will be the stress amplitude, you understand this will be 16 TA by pi d cube, and this comes out to be, if you put the values, it will be 10.2 into 10 to the power 5. Well, I advise you that whatever I am calculating over here, you please have a check. I hope I am not making any mistakes in the calculations. Pi d cube, this comes out to be something like that as 15.3 into 10 to the power 5 d cube megapascals. So, what we will be doing, that in this case sigma, oh sorry, this is not sigma, this will be your shear stress. So, tau endurance limit for material will be how much? First, everything was remaining same as we have assumed, only a load factor will come into picture. So, this load factor, as you know, it is 0.577, and so this comes out to be something like an 115.1 megapascal. See how a drastic change in the values due to so many factors that is affecting the this is coming into picture due to the design in the fatigue mode. Similarly, you can have the fatigue stress concentration factor KFS, S stands for the shear. So, that is 1.98 into 1 point, how much we have taken, KT 1.48 minus 1, that comes out to be 1.47. So, now what we do is that we take the concept of equivalent fatigue stress as we have discussed, so that the equation can be written in this way: tau equivalent, you remember it will be tau yield point divided by factor of safety yield point. If I use a Sodaba criteria, then this comes out to be like that. So, tau m plus, I remember, I hope that you understand what I am writing, because this we have already discussed, that equivalent concept. So, Fs, again you see we are multiplying only the amplitude, stress amplitude part, but not the other thing. Other thing means the mean stress. So, tau this one. So, you put the values of all these things, and 1.5, 1 point, sorry, this is not 1.5, it was coming out to be 15, okay, 15.3 into 10 to the power 5 d cube plus 10.2 into 10 to the power 5 into 1.47 into what we shall take for the tau yield. Now, let us take tau yield to be 460, you know, if I use a von Mises criteria, just simply you multiply by either 0.5 or to be on maximum shear stress, let us multiply by 0.57. So, this gives approximately value of the tau yield point, and this already we have seen that comes out to be 115.1. Of course, the dq part is there. So, this comes out to be equal to 49.88 into 10 to the power 5 divided by dq. Similarly, sigma equivalent in the same manner, if we put the values, it comes out to be 271.38 into 10 to the power 5 by dq. You know tau equivalent, you know sigma equivalent. So, one can very well utilize the Mohs circle concept to get the values of sigma 1 and sigma 2, and you can see that if we write down such values, I am not calculating because we have already learned how to calculate the sigma 1 and sigma 2. So, this sigma 1 comes out to be 280.3 into 10 to the power 5 divided by d cube, and sigma 2 comes out to be minus 8.88 into 10 to the power 5 by d cube. So, once I know this sigma 1 and sigma 2, then maximum shear stress theory, all right, ductile material, very well it can be utilized. Sigma 1 minus sigma 2 equals to sigma yield point divided by n, n is a factor of safety. What is this value? 460 was a sigma yield point value and 1.5 factor. Put these values over here, these values over here, you get the value of diameter turning out to be around 45.52 mm. Of course, you will choose a next one. If you are using von Mises criteria, then what you get? You remember it will be sigma 1 square minus sigma 1 sigma 2 sigma 1 sigma 2 plus sigma 2 whole square, and that comes out to be sigma yield point by n whole square. So, this will give you, if you put these values accordingly, it will give you equals to something like that 45.3 mm. You can see that maximum shear stress theory is coming out to be the most conservative one compared to this one. So, this ends our idea of how we calculate the diameter or the machine member dimensions based on the fatigue. Thank you.